Right, so last time we were talking about differentiability, and we had our definition of what it meant to be differentiable at a point. The point had to be in the interior of the set you're dealing with in order to define a two-sided derivative. I mentioned the notion of a one-sided derivative, and it was not my plan to talk about one-sided derivatives, but I note that one of my examples, when we looked at the example of square root x, this was only defined for non-negative x. So when I said it's not differentiable at x equals 0, of course I meant because there was this infinite limit of quotients. But another reason that it wouldn't count in this module is that the function wasn't even defined to the left of it. You can fix that by giving it a suitable definition on the left. And you could also ask about a one-sided derivative from the right on this one. But I guess square root of x wasn't the best example. The modulus function, which we looked at a bit later, was a genuine example of a function that was defined on both sides of the point and continuous, but still not differentiable at the point. I mentioned this very strange function of Weierstrass that was continuous and yet didn't have a derivative anywhere. Very unpleasant. And then I reminded you about the product rule and the quotient rule and all that stuff that you've known for ages, including the chain rule, which, as I've said, actually, if you do a rigorous, careful proof of the chain rule, you have to be careful. There's a very good false proof around, and you have to watch out for it. But fortunately, you don't have to know the proof of the chain rule in this module. Which brings us on to section 10.2. Fermat's theorem, Rolle's theorem, and the mean value theorem. Actually, Fermat's theorem, this is not Fermat's last theorem, and nor is it Fermat's little theorem. This is Fermat's theorem on stationary points, whose name is not so well known. And quite often in this sort of lecture course or module, people prove Rolle's theorem directly without proving Fermat's theorem first. But I decided that Fermat's theorem deserves a little bit of space on its own. Apart from anything else, it makes the proof of Rolle's theorem shorter if you can quote the Fermat theorem. So we're going to do all these proofs properly in full, and you'll see how to use these theorems to deduce interesting things about functions as well. So we're going to start by proving rigorously a result that you've known forever. Well, at least since A level. So what's this? This is about stationary points. The idea is that if you have a local maximum or a local minimum, that the function should have derivative 0 there. But actually, we know you have to be careful because the modulus function has got a minimum at the origin, but wasn't even differentiable there. So obviously, it's not enough to have a local maximum or a local minimum. You need to be differentiable at that point as well. And that's enough. So here's one of the ways of stating Fermat's theorem. Suppose you've got this function defined on some interval, and you can think of this as sort of a small interval around the point because you're going to be talking about a local maximum or a local minimum. And now you've found a point between A and B where the function is differentiable. And part A says, suppose that it's a local maximum. In fact, it's sort of a global maximum on this interval, but it might be that you're using this where the function is defined elsewhere as well, which would mean you'd be dealing with a local maximum. But OK, so this one is that f has a local max at C, and this is that f has a local min at C. Or you can think, I mean, if you say the function is only defined on that interval, then it's really a global maximum and a global minimum. But you normally apply this result for local maximum and local minimum. So, of course, before the proof, we can have a picture, just to remind you what's going on. So if we're dealing with y equals f of x, and you found a maximum here, you expect to find derivative 0, or if you've got a local minimum, you expect to find derivative 0 there. But as we've already observed, you need differentiability at the point you're dealing with. If you didn't know you were differentiable at that point, then otherwise you could have trouble for example, with f of x equals mod x, which shows that you can have even a global minimum at a particular point, but not have derivative 0 there because it just, in the cases where you're not differentiable. Now, I don't know if you've seen a formal proof of this or not before. It's a very quick formal proof, but I do want you to see what a formal proof of facts about differentiation look like. So here's the proof. Obviously, A and B are similar, so we'll just prove A, and B is similar. So I'll just remind you what we're given, okay? F is defined on the closed interval AB. We don't even know that it's continuous there. It could be a pretty horrible function. But we are told that F is differentiable at C. And for all other points, for all other x in that interval, okay, of course, C is in AB. And we're given that f of x is less root to f of C for all x in that open interval. That's what we're given. Now, we know f primed of C is a real number f prime of C is equal to the limit as x tends to C of f of x minus f of C over x minus C. We know that limit exists, so that's equal to the limit from the left and the limit from the right. So the limit from the left and the limit from the right are both equal. They're both equal to f prime of C, and we're going to try and prove that f prime of C equals 0. Well, let's start by considering the limit from the right. To do that, we'll look at x in the interval where x is greater than c. So first consider the limit as x tends to c plus. Okay, I don't think I need to put that stuff in. Let's just say that we'll just first consider the limit as x tends to c plus. So for x in AB with x not equal to c, because of course you have to consider x not equal to c. Oh, sorry, we'll have x greater than c, in fact. We have x minus c is, of course, greater than naught. That's the denominator. But also, since f of x is less equal to f of c is given, f of x minus f of c is less equal to naught. So, when you divide by the positive number x minus c, that quotient is less equal to naught as well. Now that's true for x greater than c, so when you take the limit as x tends to c plus, which is of course f prime of c, that's the limit as x tends to c plus of f of x minus f of c. Let's put that on the next page. Limit as x tends to c plus of f of x minus f of c over x minus c is then less equal to naught. So that shows the derivative is less equal to naught, and I do the same, exactly the same to show it's greater equal to naught, but I'll just do it in full. So similarly, but I'll do it out in full for you. For x in the open interval AB with x less than c. So we want to take the limit from the left this time. We have x minus c is smaller than naught this time. And f of x minus f of c is still less equal to naught. Remember, f of c is still the maximum value, so f of x minus f of c is still less equal to naught, even though x is less than c now. So when you divide them, it ends up greater equal to naught instead. And now you take the limit as x tends to 0 minus x tends to c minus and again, we know that that limit equation is still going to give you f prime of c. At this time, the limit of quotient is greater equal to naught. So now we've shown that f prime of c is less equal to naught and f prime of c is greater equal to naught, so it must be equal to naught. So combining f prime of c smaller equal to naught and f prime of c greater equal to naught gives f prime of c equals naught. And we've finished. Any questions about that proof? So tell me again, why doesn't that proof apply to the function f of x equals mod x? Well, OK, that has a minimum instead of a maximum, but same thing. So why can't you use a proof like that to work with the function f of x equals mod x? What did we use here that was something better than what ModX had? ModX has an absolute minimum at the origin. But it's not differentiable at the origin, exactly. So this argument becomes invalid if f prime of c isn't defined. Notice that we used, crucially, that f prime of c existed and was equal to the limit from the left and was equal to the limit from the right. And we used that in the proof. And that's false for ModX. ModX, the limit from the left, when you look at the derivative at the origin, the limit from the left you get minus 1, the limit from the right you get plus 1. They're not equal, and that's why this argument breaks down. So note this argument breaks down if we do not know the both one-sided limits existed at equal. Okay, so problems with ModX at the origin. Right, still, we've got Fermat's theorem now, so let's go on and prove Rolle's theorem. What's Rolle's theorem? This is something you were told last year in calculus. Rolle's theorem is a special theorem about functions which are differentiable on an interval and take the same value at both ends. Well, we'll give you the full conditions in a moment because you need the full force of these conditions to make it work. But we will also need to use the boundedness theorem, which we've talked about quite a lot. We've talked about it in the sequentially compactness and continuous images bit, and we also had a good go at it in one of the examples classes. So we know quite a lot about the boundedness theorem by now and when it breaks down. And because we know when it breaks down, we know that the conditions in this next result are very important. But the boundedness theorem says that if you've got a continuous function, this is for just the old version from last year, you've got a continuous function defined on a closed and bounded interval, AB, then it will achieve a maximum value and a minimum value. So that'll be the minimum value here at f of p. And there'll be a maximum value when it gets to f of q. That's the least value and the greatest value taken on that closed interval. So as far as that interval is concerned, they're a global minimum and a global maximum. But so here's Rolle's theorem. And we'll, of course, start with a picture to show you what's going on, just to remind you. So you've got a couple of real numbers, a and b, with a less than b. You've got your function defined on your closed interval AB, real valued. It's continuous on the whole of the closed interval to stop something daft happening at the endpoints, but you only require it to be differentiable on the open interval, which is actually the most we could demand in this module because I'm not talking about one-sided derivatives. If you wanted to allow one-sided derivatives at the endpoints, sometimes people talk about being differentiable on a closed interval. If they talk about differentiable on a closed interval, they mean that at the endpoints they've got one-sided derivatives, that the limits from the appropriate side exist. But we don't need that in this module. So you've got that, and then you assume that it takes the same value at both ends of the interval. Then somewhere strictly between the endpoints, it must have derivative 0 in at least one place, not all places usually, but at least one place. So we start with the diagram as usual. So it's the optional diagram. So here's your function. Here's A, here's B, and let's have a horizontal line here. So this is y equals f of A equals f of B. So it's got the same value at both ends. Then your function, it might go up a bit, it might go down a bit. You don't know what it's going to do, but it's got to get back to where it started in height. The one I've drawn here has got two places where the derivative is 0. So you could choose either one of them. And there you are. There's at least one point C, we claim, between A and B, where informally speaking, and this is going to be relevant in the next example, the next result, informally speaking, you say, okay, the derivative is 0, so the tangent is horizontal. Tangent is a tricky concept. There are some very unpleasant functions around there. Tangent lines can cross the curve infinitely often, I must warn you. Tangent lines can be a lot worse than you think if your function is horrible. But generally speaking, nice functions, tangent means what you think it is, and tangent will be parallel to this horizontal line here when the derivative is 0. So it's, remember, it's exists C in AB with f prime of C equals 0. At least one. In this diagram there are two. You don't really know what the function looks like, so you have to do a general proof that's going to be valid for all cases. So proof. I'll just remind you, all we know is that the function takes the same value at the endpoints, it's continuous on the closed interval, and differentiable on the open interval. Well, we start by applying the Boundedness Theorem. By the Boundedness Theorem, since f is continuous from AB to R, there are P and Q in AB such that for all x in the interval, in the closed interval, we have f of p less than equal to f of x less than equal to f of q. Now, it would be nice to say, and now we apply Fermat's theorem to say that the derivatives must be 0 at those minimum and maximum points, and then finish, except it's not true. Why not? Why can't we just apply Fermat's theorem and say, at the maximum or the minimum value, the derivative must be 0? What's the problem? Where's C supposed to be, for example? Where are we looking for C?
In the open.
C is supposed to be in the open interval, but we don't know that P and Q are. As we know, functions can sometimes take their greatest value on an interval at the endpoints, or the least value could be at the endpoints. So possibly P or Q are at the endpoints. However, we do know that f of A equals f of B, so if both of them are at the endpoints, then the maximum and the minimum value will be equal. What happens to a function where the maximum and the minimum value on the interval are equal? Well, it has to be constant. And constant functions are not a problem. So case 1 is that f is constant. In this case, any C in the open interval will do. So f prime of x
is equal to naught for all x in the open interval. So any c in the open interval will do.
Right. Well, that's a very, very special case.
But in any other case,
F prime of P will be less than, F of P will be less than F of Q.
so case 2, otherwise, F of P is less than F of Q.
But since F of A equals F of B,
at the endpoints, the function takes the same values.
we can't now have both F, P and Q at the endpoints. So at least one of P and Q must be in the open interval. Now, it doesn't really matter which. The proof is the same in either case.
So let's say without loss of generality, because the proof is the same in the other case. We may assume that P is in the open interval AB, but then take,
So I've assumed that it gets a minimum somewhere, minimum value somewhere, strictly between A and B. If it's a maximum, you just do exactly the same thing.
then you take C equals P, and Fermat's theorem now applies.
Why can we apply Fermat's theorem? Because now C is strictly between A and B, and the function takes its minimum value there, and it's differentiable there, because we know we're differentiable on the open interval.
Since f is differentiable at C, and f of x is greater or equal to f of C for all x in the closed interval even, but we only need the open interval, we have f prime of C equals 0.
And we're finished. You can fit, or you could do it as 3 cases. I've done this as 3 cases in the past. Constant, minimum is below the line, maximum is above the line. You can do those 3 cases separately, and it works just as well. Any questions about the proof of Rolle's theorem? So what are we doing here? We are proving intuitively obvious facts, things that you've known for a long time, things that you were told in first year, but we're seeing how to prove them rigorously from definitions, because maybe you didn't see proofs in full from definitions in first year. It varies, depending on who's teaching calculus, how many of these proofs you get given in a careful way. Now, once you've got Rolle's theorem, you can generalize it to get the mean value theorem. The mean value theorem, Rolle's theorem is like a special case of the mean value theorem, but we always prove Rolle's theorem first and use it to prove the mean value theorem. So what's the mean value theorem? Mean value theorem has very similar conditions to Rolle's theorem and a rather similar diagram. So again, you're continuous on the closed interval and differentiable on the open interval. That's the most you can ask for in this module. But now you don't assume it takes the same values at the endpoints. And if you don't assume it takes the same values at the endpoints, then you don't expect to find derivative 0 in the middle. So the best you can do is hope that the tangent at some point will be parallel to the chord joining the endpoints. That would generalize what we had before. So again, we'll draw the picture. This thing here, this condition here, that's the same as saying that f prime of c is equal to f of b minus f of a over b minus a. That term there is the gradient of the chord joining the endpoints. So that term there, that's the gradient of the chord joining the endpoints, which I'll draw in your picture in a minute. And this one is the gradient of the tangent at the point C. So again, we're talking about a tangent being parallel to a chord on the curve. Again, a tangent is a slightly risky concept, which you may want to find out about just how bad it can be. But that's how we think about it. And again, that's what the picture shows. So this time, so again, you've got A and B, but this time you've got different values. So here's f of A. Now f of B is slightly different. And I'll draw the line here. This is a line with gradient f of b minus f of a over b minus a. You can work out the exact equation for that line if you want. It's a straight line. And that will come into the proof in a minute. Let's actually have the function. Here we go. So again, just like Rolle's theorem, it might go over that chord, it might come under the chord. So I've done a very similar diagram to last time. This is y equals f of x. And now you're looking for some place where the tangent is parallel to the chord. In this case, again, there are two places where the tangent ends up parallel to the chord, and I'll again choose the one over here. So again, this is, there exists C in the open interval AB with f prime of C. So that's got gradient f prime of C. F prime of C should be equal to the gradient of the chord, the other straight line I've drawn there, f of b minus f of a over b minus a. The diagram makes it look obvious. It becomes then an intuitively obvious fact, but we've got to use our definitions and prove it rigorously, because this is rigorous differential calculus. And we're going to really check it's true, that we're not assuming that the function is nicer than it is, because this type of sketch is a sketch of what a nice function looks like. But what about functions that cross their chord infinitely often, involving functions like sine of 1 over x with sort of, there are functions around like x squared sine 1 over x, which you can add the value 0 in at the origin, and they still differentiable at the origin with derivative 0, and the tangent line crosses the curve infinitely often, and they're pretty horrible. So what I want to check then is that even if it's one of the nastier differentiable functions, the result is still true. And the proof is actually, this time, there in the printed notes, but I'll talk you through it. So the idea is that we'd like to use Rolle's theorem, but we can't yet because it doesn't take the same value at the endpoints. But if we subtracted off a very easy function, like constant times x, for example, would do it, slightly different version coming in the proof, but if you subtract off an appropriate constant times x, you'll get a function that does take the right values at the endpoint. What kind of function do you need to subtract off? It's a function, you can subtract off any straight line function like the one I've got drawn here. If you subtract that function off, you'll actually get a function which is 0 at a and 0 at b. And it so happens that a straight line function with gradient f of b minus f of a over b minus a is very easy to differentiate. So we can convert this into Rolle's theorem. I mean, informally, pity that the screen doesn't turn. If I turn my screen around, unfortunately, the big screen won't turn. But of course, if you turn this diagram through a slight angle, it actually looks like the diagram for Rolle's theorem. So you could almost say, prove it by rotating the page. But we won't do that. What we're going to do is subtract off one of these straight line functions to convert it into Rolle's theorem instead. So first of all, we define the gradient we're looking for. This is the alpha. That's the gradient of that straight line chord that I showed you. And now we do g of x equals f of x minus alpha x. And I claim that now g is just as nice as f ever was. It's still continuous because alpha x is alpha is just a constant. Notice that alpha is a constant here on the interval. So when we differentiate it, it's going to not do very much. Alpha times x people do sometimes get confused about this, but alpha is a constant in this proof. So f of x minus alpha x is a rather easy function. Alpha x is continuous and differentiable everywhere. So subtracting off alpha x is not going to change the fact that you're continuous or differentiable. So you're still continuous on AB, and you're still differentiable on the open interval. And of course, when you differentiate g, you get the derivative of f minus the derivative of alpha x. And the derivative of alpha x is alpha. Come back. Derivative of alpha x is alpha. So g prime of x is going to be f prime of x minus alpha, valid on the open interval AB. Now I claim that g does satisfy the conditions of Rolle's theorem. That's what we were up to. We were subtracting off this constant gradient function, and I claim that it now satisfies the conditions of Rolle's theorem. Why is that? Well, let's work out what g of b minus g of a is. It's f of b minus alpha b minus, in brackets, f of a minus alpha a. I've just substituted in. Rearrange that a bit, and you get f of b minus f of a minus alpha times b minus a, but that was exactly chosen. Alpha is supposed to be the right gradient. Remember, alpha is the gradient of the chord. Alpha is equal to f of b minus f of a over b minus a. So multiply by b minus a, and you get f of b minus f of a. So this thing is 0 here. So if g of b minus g of a is 0, then g of a is equal to g of b. So g satisfies the conditions for Rolle's theorem. It's continuous on the closed interval, it's differentiable on the open interval, and it's got the same value at the endpoints. So Rolle's theorem applies, and there must be somewhere in between where g has got derivative 0. So somewhere between a and b strictly, g prime of c is 0. But we know what g prime of c is. We've got a formula for g prime, that's up here. G prime of x is f prime of x minus alpha, so g prime of c is f prime of c minus alpha. So if g prime of c is 0, f prime of c is alpha, and we've finished. And that's the proof of the mean value theorem. Any questions about the proof of the mean value theorem? Okay. So we've had 3 serious, rigorous proofs. Let's see what you can do with these things. Here's a reminder about monotone functions. Monotone functions, I've got the definitions in the notes here, but you know these. Monotone functions are ones that are either non-increasing on the interval you're working in or non-decreasing throughout the interval you're working in. It's not allowed to change from one to the other. So for it to be monotone, then throughout the interval, it's either got to be non-increasing or non-decreasing. And then there's strictly monotone, which means that it is either strictly increasing or strictly decreasing. So I'm going to assume that you pretty much remember what monotone functions are. Here's some formal definitions for you, but let's not too worry about that. You can call functions like that monotonic or monotone, it doesn't really matter. And then you've got strictly increasing, strictly decreasing, and so on. And I could draw you some pictures. There's an interesting function that's worth knowing about, e.g. f from r to r, f of x equals x cubed is strictly increasing, even though it's got derivative 0 somewhere. That's turned up in some exam papers occasionally. So definitely an example worth remembering. Here's a function that's strictly increasing. As you go from left to right, the values go up strictly, even though it's got derivative 0 at the origin. Having derivative 0 at one point doesn't stop you being strictly monotone if the derivative keeps the same, is strictly of the other side everywhere else. So that one point where the derivative happens to hit 0 doesn't stop it being strictly monotone. As you can see, if you go from left to right around this curve, the functions do strictly increase. And the fact that it's got one point where derivative 0 doesn't affect anything. So, of course, f of x equals x squared is not strictly monotone on the whole real line, but it is strictly monotone on each of the half lines, a negative real axis or the positive real axis. So sometimes functions have got regions where they're monotone and other regions where they're not monotone. So what does the mean value theorem tell us? It tells you all the things that you already know from calculus. And the proofs are quite easy. And I'll give you a brief summary of how these proofs work before we go on and do a slightly more interesting example to finish the chapter. So if the derivative is non-negative on your open interval, then the function is non-decreasing. You know that. That's what you did in calculus. If your derivative is non-negative, the function can't suddenly go downwards if you're working on an interval. If your derivative is constant throughout the interval, if the derivative is 0 throughout the interval, then the function must be constant. All these intuitively obvious facts, when they're proved in rigorous differential calculus, they get proved using the mean value theorem. You might say, well, why don't we use integration? Well, in the next lecture, the last lecture, we're going to see that there are some issues with integration. In fact, not every function can be recovered by integrating its derivative. So just because the function is differentiable doesn't mean that when you integrate its derivative, you get the function back again. You need to know a bit more about the derivative than that. So you have to be a bit more careful. So since we're not allowed to use integration, our only tool available is the mean value theorem, and that's what we'll use. And similar things for strictly monotone. If the derivative is strictly positive on an interval, then the function is strictly increasing there. So how do you prove this sort of thing with the mean value theorem? Well, you take a pair of points x and y in your interval, and you want to compare the values there. And you notice that f of y minus f of x by the mean value theorem is going to be y minus x times the derivative somewhere in between. You don't know where your value in between is. You don't know which c it is, but it's somewhere in between. And if you know all the f prime of c's are 0, then you're going to get f of y minus f of x equals 0. If you know that f prime of c is greater or equal to 0, then you're going to get f y minus f of x is greater or equal to 0, and so on. So that's how you use the mean value theorem to prove those elementary things. But let's see let's see what how you use the mean value theorem to prove something a little bit more interesting. So we conclude this chapter with one more application of the mean value theorem. And there was a question quite like this on the exam last year with a different function. So, and I have to say, people did it very well. I was very pleased with what I saw last year on the exam in the mean value theorem example. So we're given a positive number b, and we're asked to apply the mean value theorem to the function f of t equals log of 1 plus t on the interval 0b. So we're taking a equals 0 here. So we're going to take a equals 0, we're going to apply the mean value theorem on the interval ab. Now, why can we do that? Because log, we know, can be difficult, but notice we're talking about log of 1 plus t here. Log of 1 plus t is perfectly nice. 1 plus t is at least 1. On 0b, 1 plus t is taking the value at least 1. Log of 1 plus t has no problems at all. It's continuous and differentiable everywhere you need it. So let's start by noting 1 plus t is greater or equal to 1 for t in AB. So log of 1 plus t is continuous on AB. And of course, we take a equals 0 here. It's continuous on AB and differentiable on the open interval as required. So this is f of t, of course. We need to know what the derivative is. What's the derivative of log of 1 plus t? Okay, well, you all know the derivative of log of 1 plus t, but you don't have to tell me. It's 1 over 1 plus t. And now we apply the mean value theorem. There exists a c in the open interval AB, which, by the way, of course, is 0b because a is 0. With f of b, which is log of 1 plus b. So log of 1 plus b equals f of b. And that's, of course, notice that f of 0 equals 0 here. So that's equal to f of b minus f of a because f of a is 0, and that's equal to f prime of c times b minus a. A is 0, so that's equal to b f prime of c, which is equal to b over 1 plus c. So log of 1 plus b is equal to b over 1 plus c. Let's put that all together. Is equal to b over 1 plus c for some c in 0b. Now, since 0 is less than c is less than b,
naught is less than 1, 1 is less than 1 plus c, is less than 1 plus b. So the other way around, you get b over 1 plus b, that's the smallest it can be, is strictly smaller than b over 1 plus c, is strictly smaller than b over 1, which is b. And that gives, by above, b over 1 plus b is strictly smaller than log of 1 plus b, is strictly smaller than b, which I hope is what we were supposed to prove. Just b of 1 plus b is less than log of 1 plus b is less than b, which is exactly what we wanted. And that finishes that chapter. Any quick questions on that example? Okay, so next lecture we do the one lecture chapter on integration. It's a quick introduction to Riemann integration, explaining some of the issues involving area and anti-differentiation, and with a few useful examples to look at.